Okay, so 6.4 inverse functions. This is notes, you guys. All right. So inverse functions, title of the chapter. What I want to look at here is a function and what happens when I send it back. So all a function is, remember, first of all, we have to go back to our definition of function. A function is simply a rule that takes a point or a value or something from an input to an output. That's all a function is. And the important thing about a function is that for any input, you get one output. Okay, so this is cool. That's fine. Oh, that's fine. The only thing that's really not okay is I can't send this point to 2 points over here. So input, output, it's like a computer, right? Computers, a computer that works correctly, every time you type in your password, it lets you into the computer, right? It doesn't decide today, oh, I'm not going to let you in unless it's broken, right? So the idea is that it's a function because you tell it what to do and it does what you tell it to do. And that's a function. So an inverse function, the idea with an inverse function is now we're going to send the values back. So if we had, again, I should have want to do this. Okay. An inverse function says, now I'm going to send the values back. The question is, where did they come from? There we go. That's what an inverse function is. We're going to send the values from what we call the range back to the domain. Okay. So let's look at this example here. This is a t-table. So if this is my x and this is my y, I'm going to make an inverse. Right now I'm going to say this is an inverse relation. Can anybody tell me the difference between a function and a relation? A while ago, right? Yes? Very good. Okay, excellent. A function is a relation, okay? But a relation is not necessarily a function. A function has that restriction where one input can't go to two places. A relation is just any way that you match up numbers. You match up something over here, and it's okay with a relation for them to be matched up in any way. So for now, I'm going to call this an inverse relation, and you'll see why. So if the function sends -2 to 0, the relation sends 0 to, what do you think? There you go. 0 goes to 1, then 1 goes to 1 goes to 4, 4 goes to 2 goes to 2, 5 goes to 3, 3 goes to 5, and here
1 goes to 7.
Okay. So that's it. Pretty much, at the end of the day, an inverse relation is swap x and y. That's really all it is. Input was over on the left. Okay. Output was on the right. Oh. Now the new relation, we switch it. Okay. This 0 here was an input. Sorry, was an output here. Now it's an input here. So we switch them. Okay. And I'm calling this an inverse relation. First of all, was this first one, was number 1 a function?
No. No.
Is number 1 a function?
Number 1's a function, but not number 2.
Correct, right? This is a function, right? Is there any question where -2 goes?
No.
No. Any question where 0 goes?
No.
1,
No.
2, 3. Okay. There's no question where any of the inputs go on t-table 1. On t-table 2, once I switch them, is there any question as to where the inputs go now?
Yes. That's a question.
There's a question. It's unclear where we should send 1. Should we send it to 0 or should we send it to 7? Okay. But basically the whole concept of an inverse relation is that you switch x and y. So let's try to figure out what the inverse of this relation would be. First of all, let's break this down. This is a relation where I take an input, okay, and what do I do to it first? Multiply by 3, and then I subtract 5. Okay? So if I were to have an inverse, okay, well, let's take a number. Okay, let's take number 1. I take that number, I multiply it by 3, and I subtract 5. What am I going to end up with? -2. What I want now is to write some kind of relation where if I put in a -2, I always get 1. Well, let's try to break this down backwards. What's the last thing we did here? Subtract 5. Okay. So maybe if I want to start with -2,
Add
Let's-
five.
let's add 5. Okay, so I'm going backwards, right? Okay, so I subtracted 5, I undid that part and added 5. Now, how can I undo a multiplication by 3?
Divide by 3.
Does this work?
Yes.
Yay! Okay. So basically what we did here, this is, my input is -2. Okay. I took my input, I added 5, and I divided by 3. So now my inverse relation is going to be input plus 5 over 3. Okay. So we're going to get a better way to do this, but I'm kind of greasing it out a little bit. Yeah.
Wait, what if you divide it by 3 first, then add 5?
No, because we're working the entire thing backwards. So we're thinking about going backwards. First thing here, we multiply by 3 and we subtract 5. So when we go backwards, first thing is we add 5, and then we divide by 3. So we go backwards and opposite. So opposite of -5 is subtract 5 is add 5. Opposite of multiply by 3 is divide by 3, and we do it in the opposite order. Yeah, it's an easier way to do this. Trust me.
When is this like used?
When is it used? So yeah.
It just
high
seems
school.
kind of like random.
So if you want, you've got a revenue function based on the amount of things that you produce, right? This revenue function tells you how much money you make based on the number of objects you produce. What if you knew at the end of the day, I want to make $100, how many widgets should I produce?
Yeah, that's
Very reasonable, right? Or time, think about like you shoot a rocket up into the air, okay? And it's going to take, and you have some kind of relationship that tells you the height of a rocket is s, okay? Based on the amount of time it's taken for it to fire, right? You have that relationship. What if you want to find out when it's going to hit the ground? So you're trying to find this given this. So it's anytime you have to ask the opposite question. A square root is an inverse function. Okay? We're going to get to that in a minute. Or probably not today, actually. But okay, so we're going to get a better way to get this function, but this is the idea. Okay? The inverse relation is y equals x plus 5 divided by 3. Okay, here's a little bit of definition for you so we actually have some notation. Okay, this is super important. You need to copy this whole page down. The note here we'll talk about, you don't have to copy that down exactly, but that first bit. Functions f and g are inverses of each other if, when I put g into f, I get x, and when I put f into g, I also get x. So basically, when I put one into the other, I get back what I started with. And it doesn't matter which way I do it. It has to be exactly x. I can't have that x not equal to 0. Right? That doesn't work. Okay? I can't have restrictions. It has to be the entire function y equals x. Okay. This notation gets a little weird. It's f to the -1. Well, I'm going to talk about that in a moment. But the notation is, I'll write it freehand just so you can see it. It's just f to the -1 power, just like an exponent. But it's not an exponent. So just be aware of that. We call it f inverse. While you're writing, I'll just make a little note here. We really should only use this if the inverse itself is a function. So that first example that I used, where I had a function and the inverse was not a function, I shouldn't use this idea because this indicates usually that the inverse is a function. It depends on who is doing it, but just be aware that there are situations where that notation doesn't really apply. Okay, so once you have this stuff written down, I just want to make a point here. And this is something, if this is a little convoluted to you, a little confusing, you're in really good company. Happens to me all the time, as a matter of fact, in calculus, where people get confused between this notation and this notation. when I'm talking about a number, let's say 3 to the negative 1, and x represents a number, so it's the same. X to the negative 1. This means 1 over x, or 1 over 3. But with a function, if I raise a function to the negative 1 power, it does not mean the reciprocal of the function. It does not. All right? It means this. It means the inverse. So you're again, if you look at this and say, what? You're in really good company. It's what we call borrowed notation, right? We borrow the idea of this negative 1 power from this idea. Okay. Typically speaking, we think of it that way. But it does not. It has nothing to do with an exponent at all. All right. So just kind of keep that in the back of your mind that when you see a function raised to a power, it means something different. All right. So let's talk about finding the inverse of another function. Okay. We could have written this like this. We could have said this is R of L. Okay. And let's find R inverse of L. Okay. In this case, I'm just saying, let's just find the relation. Let's find the inverse relation. Okay. So here's what you're going to do every single time. This is so we don't have to think backwards, right? Okay. If I want to send L back to R, this sends L to R. Let's send R back to L. That's what we want to do. Okay. So what we do here to find the inverse is the first thing we do is we swap the variables. Okay. Actually, tell you what. Let's change this to x and y. The R and L is going to be confusing for us. 3 over 8. I pulled this from another problem, and it's actually going to be easier to do it with x and y. So the first thing we do when we're trying to find the inverse relation is we swap the variables. Okay. So we had y equals 3/8 x minus 5. Now we swap and we get, so number 1 is x equals 3/8 y minus 5. And now we solve for which variable? What do we usually solve for? Sorry, with the function. We usually try to get y isolated. So here we're going to try to isolate y. Okay. So can we solve for y? Can we isolate y? How do we do that? What's the first thing we do? What do we do? Add 5. Add 5 to both sides. I get x plus 5 3/8 times y. Okay. Now what do? Multiply by the reciprocal. So I have 8 over 3. 8, 3. And we're left with y equals 8/3. So the inverse of this, of y equals 3/8 x minus 5, is y equals 8/3 times the quantity x plus 5. Now you can check a number, right? If I put a 2 in here, just to choose a numbers. Okay, if I put a 2 in here, I get 6/8. What do I get? 6/4 minus 5, 14/4. Negative 14/4, which is kind of silly to say. Is that right? What happens if I put that back in here? Yeah. I should get, what number should come out? 2. Okay? So if I put a 2 in here, okay, whatever comes out of that, if I put that back into the inverse, I should get back what I started with. Wow. Sorry? Sure. You mean go backwards? It was going to be over a fraction?
I thought it was going to be different.
This fraction here, you mean? Oh, this? It's possible that I made a mistake. Oh, yeah, you're right. 3 over 4 minus 20 over 4. Yeah, not 6 over 4. 3 over 4 minus 20 over 4 is negative 17 fourths. Thank you. Better? Yeah. Good. Okay. And again, if I put in negative 17 fourths right here, okay, negative 17 fourths here, I get 8 thirds, negative 17 fourths plus 5. Well, that's 20 fourths. So we get 3 fourths times 8 thirds. 3 fourths times 8 thirds is, okay. So this function and this function are inverses of each other. If I were to plug anything in here, okay, and plug the output back in here, I'm going to get back what I started with. If I plug in anything in here and plug the output back into here, I get back what I started with. That's what this statement says here. If I plug something into G and I plug that output back into F, I get what I started with. And if I plug anything into F and I plug that output back into G, I get what I started with. Doesn't matter which way I go. Okay, if I plug one in and I chain it, right, I do a composition back into the other, I always get back what I started with, no matter what I started with in the beginning. So this idea here is a way of saying something that's hard to say otherwise, but you're not going to use this statement very often to show things. There's a couple homework problems where we ask you to do that, but in general, this is a way for us to articulate what it means to be an inverse. It's not a formula that you use very often. Okay, let's take a look at a nonlinear function. Okay, so far we've gotten situations where we had, y equals ax plus b. But let's look at something that's not linear, okay, and figure out what's this going to do. What's this going to look like? Okay, so what do we do whenever we're trying to find a inverse? The first thing we do is swap. Okay, so here's the inverse. So we're going to go, okay, x equals y cubed. Now we try to solve for y. How can we solve for y in this case? Something we just did some in the last couple chapters. Okay, how can we solve for y? Not a square root, but a cube root. So y equals the cubed root of x. Okay, that's pretty straightforward, right? So that means if I use the function notation, that if f of x equals x cubed, then f inverse of x equals cubed root of x. So that's how we use that inverse function notation. So if I cube something and then I take its cubed root, what do I get back? If I cube 2, what do I get? If I take the cubed root of 8, what do I get?
2.
Okay. If I cube negative 3, what do I get? Negative 27. If I take the cubed root of negative 27, what do I get? Right. And if I start with 8 and I say, well, okay, if I take the cubed root of 8, what do I get? If I cube 2, what do I get? See how this is working? If I put something into the inverse, okay, I get an output, and then I put that back into the original function, I get back what I started with, and vice versa. It doesn't matter which way I do it, I will always go back and forth and back and forth and back and forth forever. Okay? So this inverse and the original are related in that way. Let's look at the graph. Graphs are fun, right? We love graphs, don't we? Okay. So, that's why it's moving so slow. Okay, let's look at the graph. So, what did we say earlier about basically all a inverse is swapping x and y, right? Let's go back to that first slide. The only thing I did here was switch x and y. Every point, the point negative 2 comma 0 is now the point what? 0 comma negative 2. The point 0 comma 1 is now the point. So basically all it is switching the coordinates. So I'm going to go ahead and pull up. This is x cubed. Okay. Let's look at an example. This is the point 1. Let's see here. It's not going to be a very good one to switch. We're going to zoom out just a touch. Okay. This is the point 2 comma, is that 5, 6, 8? 2 comma 8. When I take the inverse, what should the new point be? 8 comma 2. So I'll do that in red. Where's that? Let's see, that's 8 comma 2. How about the point 1 comma 1? Where should that go? Oh, it's the same place. Okay, 1 comma 1 is in the same place. How about the point 0 comma 0? Same place. Negative 1 comma negative 1. How about the point negative 2 comma negative 8? Switch them. Negative 8 comma negative 2. So negative 8, negative 2 goes there. Okay. Well, let's see. 3, we said what a point on this graph, on the original, is up here somewhere. It's 3 comma 27. When I take the inverse, what's that become? So it's way over here somewhere, right? Okay. So the shape of this red one is going to be kind of the same except sideways. Let's see. So we can actually do that on here, which is awesome, right? Do a new equation. We'll have this be x to the 1/3. And there it is. Okay. Let's see if we can. Those are my two functions, right? The original one and the new one. How, in terms, picturally, graphically, how are they related?
It's like it's tipped.
Not tipped, right?
But also like flipped.
Tipped and flipped. Okay. Yeah, that's a good way to put it. Okay, so again, maybe it's hard to see here. We have one function like this. Okay, I'm sorry, bad picture. I probably shouldn't have color meant to do it. One's like this. Okay, and one is going like this. Okay. So, I want to show you a line here. There's a really interesting line that I just want to call your attention to. Okay, that's not working. Okay, what line is that? It's y equals x, right? What happens if I take the inverse of this point here, 5, 5? Okay. How about the inverse of 10, 10? So one thing about the inverse of y equals x is what? Same. So any time that you're flipping a coordinate, the one interesting function is this one function here, which does nothing. Okay. What happened? Remember the point on the line here, this point here, 1, 1 on the original function. What happened to that? What happened to point 0, 0? Negative 1, 1. Negative 1. Right. So something interesting about that one. When we're talking about a graph, okay, basically what we're doing, the graph is going to flip over the line y equals x. So we're going to flip it over, right? Flip over the line y equals x. Let's look at another function here just to give you an idea. Let's talk about the inverse of y equals x squared. Okay, what should this be? We switch the variables, and now we solve for y. How do we solve this?
Square root, what's that?
Square root both sides, so we end up with y equals what?
Square root of x.
Square root, but we're actually missing something. It's kind of interesting. Plus or minus. Now, This is kind of weird, I have to say, because this is really two functions. This is the function y equals root x, or y equals. Oh, that's kind of weird, right? If I try to put this in my calculator or in a computer on a on Grapher here, for instance. Oh, y equals x squared. There's y equals x squared. Now if I flip it over, and this particular computer can do the complete inverse is what we call it. Oh, wrong. Okay. Here's what happens when I flip over that line. I started like this, and then I flipped it this way. I just want you to notice something about this new function, this new relation. Does y equals x squared pass the vertical line test? This one.
Yeah.
Okay. Does the inverse pass that test?
No.
No. So this inverse is what? They say what? Not a function. This is only a relation. So the point I want to make here is, yes, this is the inverse of this. But this is not a function. Okay? So the inverse of y equals x squared is not a function. Okay? Because I would have to write it as two functions. Is this a function? Yes. Is this a function?
No. Yes. Yes.
Okay? This function
Yes.
looks like this. This function looks like this.
Ooh.
There you go. Okay? You get the complete